Introduction to Robotics, Inverse Kinematics example. Here we are considering another example. This is a planar 2 degrees of freedom robotic arm. It has two joints, one prismatic and one revolute. A prismatic is this joint, so it will be, this link will be translating in the Z0 direction, and we have a revolute joint. This is where this link here, which has a length of L, will be rotating with an angle of theta 2. Here we already have the frame assignment done. Frame 0, frame 1, for frame 1, we have the Y direction into the page, not shown here. We have frame 2, the Z2 is out of the page, and Z3 is out of the page for frame 3, which is attached to the end effector. We have D1 is a variable joint for the prismatic joint, and L is constant, and theta 2 is another joint variable for joint 2. And we are required to perform both the forward kinematics and the inverse kinematics for this simple 2 degrees of freedom robotic arm. Here we're going to start with the forward kinematics. In the forward kinematics, first of all, we need to determine the DH parameters. So starting with the link length A, so starting with A0. A0 represents the distance along X0 between Z0 and Z1. Z0 and Z1 are coincident or parallel to each other along the same line. So X0 is going to be 0. Now for A1, A1 is the perpendicular distance along X1 between Z1 and Z2. So this is Z1 here. We agreed that Z2 is out of the page. They both intersect at the same point along the X1 direction. So A1 is going to be 0. A2 is the perpendicular distance along X2 between Z2 and Z3. So you can see that this perpendicular distance is equal to L. Then we're going to look at the link twist, starting with alpha 0. Alpha 0 is the angle about the X0 between Z0 and Z1. And since both are parallel and they remain parallel during the motion of the robotic arm, this is going to be 0. And then alpha, for alpha 1, this is going to be the angle between Z1 and Z2 along about X1. So Z1 is upwards here, Z2 is out of the page. So the angle between Z1 and Z2 is going to be 90 degrees, positive 90 degrees. So according to the right hand rule, you need to have your thumb pointing toward the X1. It's going to remain like that, pointing about X1. You have your fingers towards Z1, your palm of your hand facing you, and then you need to rotate or curve your fingers towards from Z1 towards Z2, and this takes you through an angle of 90 degrees. Then finally, we're going to look at alpha 2. Alpha 2 is about it's about X2 between Z2 and Z3. And Z2 and Z3, both of them are pointing out of the page. They remain like that, so the angle between them is going to be 0. Now let's look at the link offset, starting with D1. D1 is going to be the distance along Z1 between X0 and X1. The perpendicular distance between X0 and X1 along Z1. So this is D1 here, which is a variable. D2 is the perpendicular distance along Z2 between X1 and X2. They are both intersecting at the same point along Z2. So this is going to be 0 here. And for D2 is the perpendicular distance along Z3 between X2 and X3. and this is going to be equal to 0 because they are both collinear and parallel and intersect along at the same point along the Z3. So this is going to be 0 here. Then finally we have the joint angles. We have theta 1. Theta 1 is the angle about Z1 between x0 and x1, and this angle is about Z1 between x0 and x1, and this is going to be constant because they remain parallel to each other and it's going to be equal to 0. Theta 2 is the angle about Z2 between x1 and x2, and this is variable and it's going to be equal to theta 2. And finally we have the theta 3 is an angle about Z3 between x2 and x3, and these two are parallel, will remain parallel, and thus it's going to be equal to 0. So these are the DH parameters for this robotic arm. The next step in the forward kinematics is to substitute for the each row into the general homogeneous transform matrix for each link. So starting with I1, and then we'll have T1 with respect to 0, the transformation matrix of frame 1 with respect to frame 0, and you need to substitute these values for theta, D, alpha, and A into this matrix. If you do this, you're gonna obtain this result here for T1 to 0. If you do it for the second row, this is the matrix that you will get. And if you do this for the third row, this is the matrix that you're going to obtain. Now, it's recommended always to double check your answers and see if they make sense or not. So if I look at the transformation matrix for T1 to 0, you can see that frame 1, compare frame 1 to frame 0, you can see that they are parallel and they will remain parallel because this is a prismatic joint allowing only for linear motion. So this part here will be the identity matrix, which makes sense. Then look at the origin of frame 1. Origin of frame 1 is translated along the z-axis, along z0 by a distance of d1. So we'll have 0, 0, d1 here. This corresponds to the x-coordinate, y-coordinate, and z-coordinate. So it makes sense, this one. And let's look at T2 to 1. T2 to 1 represents the orientation and position of frame 2 with respect to frame 1. You can see we have XY here, but we have X and Z here. So we have not one basic rotation, but rather two basic rotations. So it will be difficult to judge this one just by inspection, but at least we can say that this is correct. The position of the origin of frame 2 with respect to frame 1 is at 0, 0, 0, 0, because they have the same origin here. And finally, frame 3 with respect to frame 2, they'll remain parallel, and this is why we have the identity matrix here, and you can tell that frame 3 is translated along the x-axis, x2, as we can see here, along x2 by a distance of L. And so this also makes sense. And it's always going to be the same according to our agreement for the frame assignment for the end effector. We always assume that the end effector frame will be parallel to the joint previous to it. Okay, the next step in the forward kinematics is to multiply the transformation matrices. So to get the transformation matrix of frame 3 with respect to frame 0, I need to multiply T1 to 0 by T2 to 1 and T3 to 2. And this is going to be simple, especially in this case where we have identity matrices hidden here. And this would be the final result. So you start by multiplying this matrix by this one, and this would be the result here, and then you multiply this matrix by this one here to get the final result of the forward kinematics. So this is a summary of the results that we got for the forward kinematics. This is the transformation matrix representing the orientation and position of the end effector frame, frame 3 with respect to frame 0. The transformation matrix consists of two submatrices. One would be the rotation matrix here, which is R3 to 0, which represents the orientation of this frame with respect to the base frame. And this here in blue represents the position of the origin of the end effector with respect to the base frame. So we have X, Y, and Z here. X being L cosine theta 2, Y being always equal to 0, and Z being equal to L sine theta 2 plus D1. And this is the orientation here. So just as a reminder, the result of the forward kinematics, it simply gives us the orientation and position of the end effector frame with respect to the base frame. So you are simply answering the question, where is my hand, or where is the hand of the end, or the end effector of the robotic arm? For us, for human beings, this seems to be a silly question. Where is my hand? Because we honestly, we don't think about this. It's done by the automatically in the subconscious, and you don't need to worry about really figuring out where's your hand before reaching out to grab another object or a certain object. Where it comes to robotic arms, no, this becomes an important task, and you need to really program it within your robotic arm. Now we'll proceed with the inverse kinematics. So this is the transformation matrix as we obtained from the forward kinematics, and this is the general transformation matrix for an end effector with respect to the base frame. We have general values here, could be any values for R11, R12, and so on for the rotation matrix. And we have here X, Y, and Z. Any specific values could be here, except for Y, of course. For this case, Y is always going to be 0. Anyhow, but we have it, we always, part of the inverse kinematics, we want to simplify things, write it in the most general case, which applies for any robotic arm, compare it to the one we obtained from forward kinematics, and you will see that X is going to be L cosine theta 2, and the Z in this case is going to be L sine theta 2 plus D. X here, and here we have the Z. Now the goal is to, from this problem, you need to figure out what are the values for theta 2 and the value for D1 in order to accomplish a certain X and Z values for the end effector. So the inverse kinematics is the opposite of the forward kinematics problem. Now you have a certain value, a desired value, or a position for the end effector, and you need to determine on the joint variables which will take you there, the D1 and theta 2 in this case. Starting with these two equations that we obtained in the previous slide, an equation for X, an equation for Z. Again, the goal is to explicitly find a relationship or expression for theta 2 and another one for D1. We're going to use two methods to solve our inverse kinematics in this lecture. In the first method, I'm going to start by looking at D1. I want to find a value for D1 as a function of X and Z and L with no dependence on theta 2. To do this, I'm going to try to square each one of these two equations and then sum or add them together. So we'll have X squared plus Z squared equal to L cosine theta squared plus this term, whole term squared. So we'll have L squared cosine theta squared plus L squared sine theta 2 squared plus 2 times L sine theta 2 D1 plus D1 squared. Now you group these two terms together And you're gonna notice that here we have a trigonometric identity which says that cosine theta 2 squared plus sine theta 2 squared is gonna be equal to 1. So and this will bring us to x squared plus z squared is equal to L squared plus 2L sine theta 2 d1 plus d1 squared. However, we didn't reach our goal. You can see that we still have both d1 and sine theta 2. So we have the two joint variables, theta 2 and d1, in the same equation. And the idea is to try to have only one joint variable first. So and our goal was to only have d1 only in this equation. Remember that x and z and L are all constants in the inverse kinematics problem. X and z are the coordinates of desired point for the end effector, and L is a physical dimension, is the length of link 2. So how to proceed? We're gonna take this equation to the next slide. And we can notice that L sine theta 2 appears in the second equation. So then it's possible to rewrite the second equation as L sine theta 2 is equal to z minus d1, and substitute the value for L sine theta 2 into this equation. So now we'll have x squared plus z squared is equal to L squared plus 2 times z minus d1, all of this times d1 plus d1 squared. This way you can see that we eliminated theta 2 from the equation, and this was our goal from the beginning. Now after a little bit of manipulation, you'll have 2z d1 minus 2d1 squared plus d1 squared, so it becomes minus d1 squared here. And I want to rearrange the equation such that I have d1 squared minus 2z_d1 plus x squared plus z squared minus L1 squared. All of this is equal to 0. It looks like a quadratic equation because it is a quadratic equation. Just keep in mind that it looks a little bit different than what we used to see in other courses, because in other courses usually the x is the variable or the z is a variable, but here z and x are known values. So this is x squared plus z squared minus L squared. All of this is like a constant here, and the d here is a variable, z is a constant, and the d is also a variable here. So this is a quadratic equation where we want to solve for d1. Now we can use the general quadratic equation formula for which we have d1 here, and then we have minus, usually we call this b, so minus the minus 2z, and plus minus under the square root we have b squared minus 4a, a is here 1, it's going to be the 1, and multiplied by c, which is s squared plus z squared minus L squared. All of this divided by 2 times a, the coefficient of the variable here. This can be simplified. The minus sign will cancel out. 2 will cancel out with the 2 here. So we'll have a z. 4z squared will cancel out with the minus 4z squared. And the 4 can be taken out of the square root to become 2 and cancel out with the 2 here. So we'll have d1 is equal to z plus minus the under square root L squared minus x squared. So the interesting thing here is that we have two solutions, one plus and one negative. And here I have in the figure a representation of the robotic arm. Here we have the length d1, which is a joint variable, the prismatic joint variable, and I have L. This corresponds to one solution, and here I have another solution where I have D and I have L. Both of them will give me the same end effector position. So the red dot here represents the end effector. The difference between, so this is solution 1, this is solution 2. The difference between both solutions is that here the robotic arm is pointing upwards. Here the robotic arm is pointing downwards. Both of them pointing towards the same end effector point. I have superimposed both solutions on the same figure here. The first solution being in orange, the second one being in blue color. So you can see they would reach the same position. So this really verifies our solution here that there will be two solutions for D1. And you can see that it depends on Z, L, and X, which are all given values. Now we need to proceed for theta 2. So if we have theta 2, the problem becomes much more, if we have D1, the problem of finding theta 2 becomes much more easier. The second equation can be written as L sine theta 2 equal Z minus D1. D1 is known value now, has a known value now. And if you take equation 3 divided by equation 1, we will have L sine theta 2 over L cosine theta 2 equal to Z minus D1 over X. And L will cancel out with the L. Sine over cosine, this is a tan. Tan theta 2 is equal to Z minus D1 over X. And thus we can find theta 2 as the tan inverse of Z minus D1 over X. Z is known, X is known, and D was found in the previous slide. So, and you can see that theta 2 depends on D1. So for it, so this is the first solution for D1. There will be a corresponding theta 2, which is in this case in the first quadrant. And for this larger D1, representing the second solution, we'll have another value for theta 2, which in this case is going to be in the fourth quadrant. Summary of method 1, we will have two formulas, two equations, one for finding D1 and one for finding theta 2. In the next slide, we're going to start with method 2. In method 2, now we're going to start looking for theta 2. In method 1, we started by first looking for a value for D1, but now we're going to start by looking for a value for theta 2. Now you can see directly from equation 1 we can obtain cosine theta 2, which is x over L. And from the general trigonometric identity, which is cosine squared plus sine squared is equal to 1, we can find that sine theta 2 is plus minus under the square root 1 minus cosine theta 2 squared. If you wish, you can substitute for cosine theta 2 here to have it as x over L, and now we have a formula for sine theta 2 and we have a formula for cosine theta 2. Now what you will see is that theta 2 will have, obviously we're going to have two possible solutions, and this makes sense also from our previous representation. Theta 2 could be, for example, in the first quadrant or in the fourth quadrant. So once we have cosine theta 2, we have sine theta 2, dividing sine by the cosine, we're going to get a formula for tan theta 2. And if you wish, you can simplify these things by getting the x over L inside the square root here, and you will obtain a formula for theta 2. So theta 2 is going to be a tan 2 plus minus, representing two solutions. In one solution we can consider the plus, and the other solution we can consider the minus. Under the square root we'll have L over x, all of this squared minus 1. After obtaining a value for theta 2, we can now proceed for looking for a value for D1. And we can obtain this from equation 2, which is the only equation that has d1 in it. So we will rearrange equation 2 such that d1 is on the left side, the right side we have z minus L sine theta 2. Theta 2 was obtained in the previous slide. So we have here a summary for the results from the two methods. From method 1, we start by obtaining d1. We'll get two possible values for d1, and then we apply the formula for theta 2 to find the two values of theta 2 corresponding to each value of d1. In method 2, we started by obtaining a value for theta 2 using this formula, and turned out to be two possible solutions. Then we substituted each solution into this formula to get the two corresponding values for d1. It's really interesting to see that the formulas don't really look exactly the same, and this is totally okay, and it makes sense. So it's not necessarily that we need to have the same expression to get the same value. It could be different expressions, but they will always talking about the same thing. So for example, if you look here, d1 is equal to z plus minus under the square root L squared minus x squared. L squared minus x squared under the square root is in reality equal to L sine theta 2. So you can see both of them are really referring to the same thing. Now, one way to really, let's say, verify your solution is to try to think about the graphical approach. And so, for example, here we look at the method 1. We have according to the formula, it says that d1 is equal to z plus minus under the square root L squared minus x squared. So let's look at it here. This is z. This is d1. What would be this small distance here? It's supposed to be, this is L and this is X. So Lx minus L squared minus X squared under the square root, according to Pythagoras, will give me this length here. So then I can relate Z to D through what? Z minus this distance will give me this distance, which is this equation. And also, if you wish, you can also find theta 2 from graphical approach. Tan theta 2 is going to be this distance, which is z minus d1, over this distance, which is x, from this right triangle here. It's always very useful, and I always recommend it, to try to relate the equations to the geometry of the problem itself and try to make sense out of it. Now, another way to verify your solution is to assume numbers. L, so we're assuming that L is going to be equal to 10 centimeters. If you want, you can assume theta 2 to be any angle. I'm assuming here that's going to be equal to 45 degrees. And I'm assuming that at a certain point in time also d1 is going to be equal to 5 centimeters. You can choose any other numbers, by the way. And then I'm going to substitute these into the result from the forward kinematics, which is the transformation matrix of 3 with respect to 0. So cosine theta 2 becomes cosine 45, which is about 0.707. Minus sine theta 2 becomes minus sine 45, which is minus 0.707. L, which is 10, times cosine 45 is going to give me 7.07, and so on. The result of the forward kinematics would be then x equal to 707 centimeters and z equal to 12.07 centimeters. Gonna take this result to the next slide. Again, I'm assuming a dimension here, which is that L is equal to 10 centimeters. I'm assuming that at a certain instance in time, theta 2 could be equal to 45 degrees and D1 could be equal to 5 centimeters. After substituting these into the forward kinematics, I got a value for X equal to 7.07 centimeters and a value for Z equal to 12.07 centimeters. I will take these values and substitute them into the formulas obtained from inverse kinematics using method 1 and using method 2. From method 1, I had a formula that gives me D1 equal to Z plus minus L squared minus X squared under square root. So if you substitute for Z with 12.07, for L with 10 centimeters, and for X with 707, as we have here. And since we have plus or minus, this will give me two values. One value being 19.14 centimeters and one value being 5 centimeters. The same method, we obtained a formula for theta 2, which depends on Z, D1, and X. So substitute for Z with 12.07, for X with 7.07, and then for D1, we're going to substitute once with 19.14 and once with 5 centimeters. When we substituted for D with 19.14 centimeters, this gave us an angle of minus 45 or 315 degrees. When we substituted for D1 with 5 centimeters, this gave us an angle of 45 degrees. So what we got here is that D1 could be 5 centimeters and with a value for theta 2 of 45, and notice that these are the same values we started with. We started assuming a value for D1 to be 5 centimeters and theta 2 to be 45 degrees. And this validates our approach. So if you started with a certain assumption for the joint variables, you went through the force kinematics, you found the corresponding position, and then you took the position and substituted that into the inverse kinematics, and you got the same joint variables that you started with. This in somehow also verifies on or validates your approach. In addition, you will see that we will get a second solution because we agreed that for this problem we have two possible solutions. Now let's look at method 2, because some of you may not be convinced that both methods are correct or both methods will give me the same answer. So let's see. We start with theta 2. Theta 2 according to method 2 is equal to A tan 2, which is tan inverse of plus minus L over X squared minus 1. L is 10 centimeters and X was found to be 7.07. This would give me two answers, either 315 degrees or 45 degrees. Now D1 is equal to Z minus L sine theta 2, Z being 12.07, L is 10 centimeters, and sine theta 2 sine of either 315 or 45. So if you substitute 315 here for theta 2, this will give you 19.14 centimeters. If you substitute 45 degrees, this is going to give me 5 centimeters. So I'm again getting the same two pairs. If D2 is 5 centimeters, I will have an angle of theta 2 of 45 degrees to reach the same end effector position of X and Z. If I had a value for the D2 being 19.14, this corresponds also to an angle of theta 2 equal to 315 degrees, and which will give me again also the same end effector position. These are corresponding to the two solutions, one having the end effector pointing upwards and one having the end effector pointing downwards. That's it for today. Thank you for listening. Take care.